really hope I get that with the internship. And they paid my relocation to the Bay Area. That's where the internship would be. Bay Area. Yeah, that'd be cool.
All right, so it's 8:30 and we're gonna cover digital to analog conversion today. So the opposite of analog to digital conversion. So this kind of describes an ideal digital to analog converter. So it's going to accept these digital inputs, which are going to be binary, right? And it's going to produce an analog output voltage or a current. So you can have either or as your analog outputs. And the assumption about an ideal one is that it has this uniform binary digital encoding. And it has unipolar output ranging from 0 to full scale voltage.
Be again for him.
You can just take whatever.
Yeah.
So our different parameters for the digital to analog converter is going to be n, your number of input bits, VFS, which is your full scale output, so the maximum voltage that you can output by the converter. And then we have, again, delta as the step size. And delta is going to be defined by the full scale voltage divided by the number of combinations that we have at the binary inputs. And then we can say that's the log base 2 of the full scale divided by the delta, which is our subinterval, well, our step size. That is going to be our resolution of the depth. Right. So for digital to analog conversion, we have a few things to cover. And first is defining and doing the delta. So delta is the full scale. And remember, full scale is again the maximum, right? And then 2 to the n, where n is the number. So if we want to create a table of how this would be in terms of inputs and outputs. So this is digital. values, right? And then we want analog as output. So if we have digital values and we just assume that they're unsigned numbers, we're going to go from 0, 1, 2, all the way to 2 to the n minus 1 is my last combination, right? So all of these values then need to be mapped to some analog value, right? So if we have 0, that means we're going to output 0, right? But we also have to include that we have this fixed step into how much we can output. We can only output these fixed analog values with the digital to analog converter. So if you want to represent 0, or really 0 through delta, which is our step size, that's what your Vout is going to be. It's all, so if you want to represent anything in this range, the output is going to be 0. And then if I give an input of 1, that's going to correspond to the range of delta to 2 delta, right? And then for 2, it's going to be 2 delta to 3 delta as the range that I am trying to reach, right? And then going all the way back to the bottom, so if we have 2 to the n, we want the range 2 to the n minus 1 delta is going to go to 2 to the n times delta, which is equal to V full scale.
That's 2 squared.
2 to the n. So we're going to be outputting these fixed values to our analog. And it's going to be that portion of V full scale. So if I'm inputting 1 as my digital value, then I would get out delta, right? If I'm inputting 2, I would get 2 delta. And that would go all the way into the end, right? So I don't ever truly output V full scale, because I have to output 0 as one of my combinations. So if we kind of simplify things, then we can just say that the output is going to be this binary weighted summation multiplied by our resolution of delta. So you just need to take the binary number that you convert, that you're taking in here, and multiply it by delta to get what the analog output would be. So here's our example. So if we have V full scale of 0.8 and n is 3, then my delta is 0.8, right? Divided by 2 to the 3, which is 0.8 divided by 8, which is 0.1. And then if my digital in is 101, 101, convert that to decimal, which is what we're used to working with, is 5, right? So 5 times delta is my output. So it's 5 times 0.1. So I would output 0.5 volts for the input combination 0, 1, 0. I mean 1, 0, 1. Okay? So if I had the input combination 0, 0, 1, I would output 0.1 volts, right? So the digital to analog conversion is a little bit simpler to compute by hand than the analog to digital conversion. And again, here it is. You just, what is the binary number in terms of decimal? Multiply it by delta. That is our outputs. And this is going back to assuming this uniform distribution. And then I do just want to show you guys the hardware that implements this. You don't have to understand this, but basically you have your least significant bits down here. And then if you have a 1, you connect it to ground. And that's going to contribute a little bit of current as well as a little bit of voltage at the output. And it's proportional to this resistor size compared to this resistor size. So if this resistor is connected, 1/8 of the voltage is going to come across here. If this one is connected, 1/4 is. If this one is connected, 1/2 is. And if this one is connected, it's proportional directly, right? So we are increasing the decreasing the proportion that the voltage scales by 2 for each one of these steps. So that's how we're getting the binary encoding, right? Because this one is basically Vref divided by R. This is Vref divided by 2R. Vref divided by 4R. And Vref divided by 8R. Okay. And that is just 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. Right? So that's how we get these different output voltages with this circuit. Yeah. Yeah, but we're dividing.
Oh,
Okay. So it's 1/8 of Vref. And then this is just 1, right? So that's why this is the least significant bits, and this is the most significant bits. So one thing about this, though, is it is simple to understand. If you knew more about the analog circuits, it is simple to understand, but it is very complicated to make. If you want something like 64 bits, you need to make this resistor that is 64 times more, has 64 times more resistance than the reference. And you have to have all these different combinations, right? Up to 64. So that is what makes it complicated to make, and it limits number of bits. So this is fine if you have this small bit width and it doesn't require too much complexity with like 3, 4 bits, 5 bits. But if you want it to scale up, then you need to use a different design. So this is the different design. It uses a resistor ladder. And all of these resistors have the same size, minus these ones up the ladder. But again, I only have 2 resistors now, 2 different sizes. One that is twice the size, one that is the normal size. Okay. And then if you do the conversion with the resistors in parallel and series, you would get that you have R here, you have 2R here, you have 4R here. And it turns out to be the same circuits in terms of the analysis of it. But now I can manufacture this very easily. So this is what people use because it's now kind of infinitely scalable, right? So those are just the two circuits I wanted to show you. So the binary weighted one is very easily understood, has that easy implementation. It's also faster than the other one. And then, well, not what I meant. It's limited, has a large different combination of registers. It's susceptible to noise, and it's expensive because it's very complicated for it to manufacture. But the R2R, just 2 register values, easier implementation, easier to manufacture, and it's faster. The only problem is it has this more complex analysis, but we only need to do this analysis once. And once we understand how it scales, we don't need to reanalyze like the 64-bit version, right? So just to finish off the lecture here, we first start with the analog value from the environment. That changes the sensor value, which is going to again be some analog value. Like a temperature sensor we mentioned is just a resistor, and it changes its resistance based on the temperature. And then because the resistance changes, the voltage across it changes. And we just have a table that says at this voltage, then this is the temperature. At this voltage, this is the temperature. So we have to use the analog to digital converter in order to take that analog value and turn it into some binary encoded value that the processor can handle. And then after the processor handles it and processes the information, we can then make a decision on how to change the environment. But in order to change the environment, we have to then convert that digital signal into an analog one so that the actuator can then modify the environment. Okay. So that's the overview of embedded systems, why we need analog to digital converters, why we need digital to analog converters, because the sensors and actuators are working in the real world. But in our processors, we have this discrete binary values that we need. So we finished with some time left, and I did print out the homework for you guys to work on for the rest of the time. Before we do that, though, I do just want to mention that our poll code for today is 132. So just answer anything, and then you have the rest of today to work on the homework 5. It's right here. And then on Friday, we'll also have time to work on homework 5. And then next week, we're going to go over how to connect sensors and actuators to the Arduino board. And we will do lab 1, where you actually connect a few different sensors and actuators to the board. All right. So do just make sure that you answer the poll. It's 132.
Just the homework.